So fourth assignment, numerical number 1. 1 liter of 0.5 normal HCl was heated so that 3.65 grams of HCl escaped, and volume of the solution also decreased by 200 cc due to evaporation of water. Calculate normality of leftover solution. So we'll calculate initial weight of HCl. For that, initial normality 0.5 is equal to weight of HCl divided by molecule weight into 1000 divided by 1 liter volume is again 1000 into n factor for HCl is 1. So from this you can calculate 18.25 grams. Now, final normality. From 18.25 grams of HCl, 3.65 escaped. So this much is left. Divided by molecular weight, no change. 1000, no change. Volume also decreases by 200. It means volume is 800. N factor, no change. N factor is 1. This is the answer. Second numerical. Calculate the mass of copper sulfate pentahydrate required to prepare 200 cc of 0.04 normal molar solution. Very, very simple numerical. Molarity 0.04 is equal to weight of solute that we have to calculate, divided by molecular weight is given 249.5 into 1000 divided by volume of solution is 200. This will be your answer. Next, numerical number 3. Calculate molality of the solution 536 grams of which contains 0.2 mole of glucose dissolved in water. See, in all my assignments, there will be mixture of numericals right from simple to difficult numericals, right? So don't think all numericals will be simple. So next numerical, weight of glucose. How much? It's 0.2 mole of glucose. 0.2 into molecular weight, 36 grams. Molality is equal to number of moles of solute into 1000 divided by weight of solvent. Weight of solvent will be solution minus solute. This is the answer. Next. Calculate molality of 1 molar solution of NaNO3. Density of the solution is 1.037 gram per cc. Say we have to calculate molality. Okay, say solution is 1 liter, 1000 cc. It is 1 molar means 1 liter of solution contains 1 mole of NaNO3. So it contains 1 mole NaNO3, that is 85 grams NaNO3 molecular weight. Its weight will be 1000 into density, so much. So molality will be weight of solute 85 divided by molecular weight 85 into 1000 divided by weight of solvent. Weight of solvent will be 1037 minus weight of solute. This is the answer. Next numerical. Calculate the concentration of oxygen sea water, 50 kilograms of which contains 1 gram of dissolved oxygen. Express your answer in ppm. So oxygen in ppm will be this is 1 gram of dissolved oxygen. 1 divided by 50 kilograms. 50 kilograms will be 50,000 grams multiplied by 1 million. This is the answer. Next, number 6. Calculate the mass of water that should be added to 91% aqueous solution of sulfuric acid, density this much, to prepare 100 cc of 30% solution of density 1.31 gram per cc. In this numerical, some data is extra that is not required, but anyways, final weight of solution. We want to prepare 100 cc solution, density 1.31. So final 131 grams. Final weight of sulfuric acid. It contains 30% sulfuric acid. So 30% of 131, 39.3 grams of sulfuric acid. Now, this much sulfuric acid will come from the initial solution, and the initial solution contains 91% sulfuric acid. So, weight of initial solution required for 39.3 grams sulfuric acid. So weight of initial solution required will be 100 divided by 91 into 39.3. Now, how come this expression? See, 91% means for 91 grams of sulfuric acid, I'll have to take 100 grams of solution. For 1, I'll have to take 100 divided by 91. For 39.93, how much I have to take? So this will come out to 43.19 gram. So weight of water to be added, 131 minus 43.19 gram. Answer is slightly different. So you can make the correction in the answer given. This will be the exact answer. 7th. Calculate molarity and molality of the solution prepared by dissolving 20 cc of acetic acid, density 0.9 in 100 grams of 100 cc of water. See, weight of acetic acid 20 cc into density 18 grams. Density is given 0.9. Now, molality. Solute 18 grams. Molecular weight of acetic acid 60,000 in both. Molarity. We need volume of solution. Volume of solution will be volume of acetic acid plus volume of water. So this is 120 cc. Denominator is weight of solvent. 100 cc of water will be 100 grams of water. So these are two answers. Now, theoretical questions. Why do we feel uncomfortable in breathing at high altitude? This you'll find in your notes that at high altitude, atmospheric pressure is low. Therefore, solubility of oxygen in hemoglobin is less. Therefore, supply of oxygen to the body parts decreases. You'll find details. Next, look here. Now, this is for the next question. Next question says, a solution of equal number of moles of liquids A and B is allowed to attain equilibrium with its vapors. What will be the relative composition of A and B in vapor phase and the liquid phase? Number of moles mix is equal. It means mole fraction is same, that is 0.5 each. Now, in the A part, it says P naught A is equal to P naught B. Now, look here. P naught A is equal to P naught B. Mole fractions are already equal. It means PA will be equal to PB. What does it mean? It means number of vapors of both the components formed will be equal. Therefore, quantity of liquid left, liquid A and liquid B left will also be equal, right? So that's the meaning of relative composition. Composition in the vapor state and composition in the liquid left will be same. Now look at the B part. P naught A is more than P naught B. It means if P naught A is more than P naught B, it means PA will be more than PB. What does it mean? It means vapors of A formed will be more than B. Due to this, composition of A in the vapor state will be more than B, while composition of B in the liquid state will be more than A, right? A left in the liquid state will be less, B left in the liquid state will be more. That's the meaning of relative composition. Third question. Define vapor pressure. How does it vary with temperature? This is directly given in your notes. Remaining A, B, C, D type questions. Right. Now we start with notes. Okay. We started with the elevation and boiling point last time. And last we did was the graph. In your register, I think graph should be in front of you. In the graph, you can see there are three plots drawn. One is for the solvent, then solution 1, solution 2. Solution 2 is more concentrated than solution 1. And also, delta TB for solution 2 is more than the delta TB for solution 1. What does it mean? It means elevation and boiling point and concentration of solution, they are directly proportional to each other. Now start writing. Graph shows that elevation in BP and concentration of solution are directly proportional to each other. Directly proportional to each other. Now you have to copy from the board. Mathematically, delta TB is proportional to molality, or I can say delta TB is equal to a constant Kb into molality, or I can say delta TB is equal to Kb. Molality we can expand. This will be Wb by Mb into 1000 divided by Wa. Equation number 2a means first equation of second colligative property. Now we'll label Kb. Kb is called molar boiling point elevation constant. There are two more similar terms used. Molar boiling point elevation constant, also called boiling point elevation constant, also called elevation constant. So there will be no confusion at all. But there's one more special term used, note down, also called EBU LLIO scopic, also called ebullioscopic constant. Ebullioscopic constant. Now for definition, we'll take the help of this expression. Remember, if molality is 1, then Kb will be equal to delta Tb. So this will give the definition. Delta Tb is defined as, means elevation constant is defined as the elevation in elevation in boiling point of solvent in the solution whose molality is 1. Whose molality is 1. Its units are K by M. We pronounce it Kelvin per molal. Kelvin per molal or Kelvin kg per mole. Kelvin kg per mole. Further item, value of Kb depends on nature of the solvent as given below. As given below. Write down one expression. Kb is equal to mr Tb squared divided by delta H VAP into 1000. Equation number 2b. I'll label it. But before that, let me tell you, this expression is very much in your syllabus. Question or numerical is never asked on this in CBSE exam, but in JEE Mains, question has been asked in the past. So this is molecular weight of solvent. This is gas constant, and the value of gas constant is 8.314 joules per Kelvin per mole. Delta Tb, boiling point of solvent. Delta Tb is boiling point of solvent. And this symbol, I hope you know, this is delta H vaporization, enthalpy of vaporization of solvent. So all parameters depend on nature of the solvent. Therefore, we say that value of Kb depends on nature of the solvent. Now, elevation is always added to the normal value. So write down boiling point of solution is equal to boiling point of solvent plus delta Tb. So value of elevation will be added to normal boiling point of solvent. Now I'm sharing one numerical. Check karo, shared on WhatsApp and not chat box. Yes. Calculate boiling point of a 10% aqueous solution of urea. Kb of water is 0.52. 10% solution means out of 100 grams of solution, 10 grams is solute, remaining 90 grams is solvent. Say solution is 100 grams. It means 10 grams is urea, 90 grams is water. Elevation will be Kb. Kb is 0.52 into 10 divided by molecular weight, 1000 divided by weight of solvent 90. When you calculate, this will come out to 0.963. See, elevation is a difference. So whether you write in Kelvin or Celsius, that is one the same thing, right? Celsius, or you can write Kelvin, that's one the same thing. So boiling point of solution, let me write in brackets for degree centigrade. It will be 100 plus elevation. Now imagine that the solution contains more than one non-volatile solute. Then what will happen? How do we carry out calculations? Look here. In this expression, this part is number of moles of solute. So what we'll do is number of moles of all non-volatile solutes will be added and substituted. So we'll modify this equation. Right on. If the solution contains, two or more non-volatile solutes, then equation 2a is modified as follows. Wait a minute. It's modified as follows. So the equation becomes delta TB is equal to KB into NB1 plus NB2 means number of moles of non-volatile solute have been added, multiplied by 1000 divided by weight of solvent. This becomes equation number 2C. We'll solve one numerical on this.
Sir? Sir, can you please get the set? Thank you, sir.
How come this is not going on WhatsApp? I'm trying to share on WhatsApp, it's not going. I'll share the photo of this numerical. It's not, I'm not able to send it. Yeah. The numerical is calculate boiling point of solution 570 grams of which contains 18 grams of non-volatile solute A, 32 grams of solute B, and dissolved in water. Kb is given. So delta Tb will be 0.52. Now, number of moles of solutes will be added. One is 18 divided by 180. The other solute is 32 grams divided by molecular weight 160. Denominator is weight of solvent. And remember, weight of solvent will be weight of solution minus weight of both the solutes, minus 18, minus 32. Clear? Both the solutes masses have to be subtracted. So this elevation will come out to 0.3. So boiling point of solution will be 100.3 degrees centigrade. So with this, we finish second colligative property. Right, on number 3, third colligative property, depression in freezing point. Depression in freezing point. Now for this, first you need the definition of freezing point. Adam, freezing point of a substance is that temperature at which vapor pressure of its solid and liquid forms becomes equal and they exist in equilibrium with each other. They exist in equilibrium with each other. So, like if we consider water at its freezing point will have solid and liquid forms of water which will exist in equilibrium with each other, and vapor pressure of both the forms will be same, that is, be equal. Next paragraph. Thus, for a pure solvent at its FP, freezing point, right on FP, at its freezing point, following equilibrium is established. So the equilibrium will be substance in the liquid form and substance in the solid form will exist in equilibrium with each other. Could this child identify, please? Who is this Abhirami?
Sir, it's me, Anish, sir. Actually, my
Okay.
tablet's not working.
Yes. Yes. Right. So this will be the equilibrium when the freezing point of pure solvent is attained. For that item, when a non-volatile solute is dissolved in a solvent, its freezing point decreases. So if we dissolve some sodium chloride in water, its freezing point will fall below 0 degrees centigrade, right? Reason for the depression in FP is given below. Now look at the board. I'll explain the reason for the depression in freezing point. Look here, don't write anything. Let us say this is the pure solvent at freezing point. There is equilibrium between liquid and solid forms of the solvent, and vapor pressure of both the forms is equal. Now, when we dissolve some non-volatile solute, let us say glucose or urea or sodium chloride, these solutes will dissolve in the liquid, not in the solid. Solid will not dissolve in solid, it will dissolve in the liquid. So when solute dissolves in the liquid, vapor pressure will decrease. But since solute does not dissolve in solid form, its vapor pressure will not decrease. It means now equilibrium will be disturbed. Vapor pressure decreased, vapor pressure has not decreased. Now to re-establish equilibrium means to make the vapor pressure of both the sides equal, we'll have to decrease vapor pressure of solid solvent. And for that, temperature has to be lowered. Remember, when we decrease temperature, remember vapor pressure of the liquid will also decrease. But vapor pressure of solid decreases very fast. So we'll have to decrease temperature and then only equilibrium will be attained, that is freezing point will be attained. Now write down. At FP, at freezing point, Vp of vapor pressure of solid and liquid forms of solvent is same. So when non-volatile solute is added, it dissolves in the liquid solvent, but not in solid solvent. Due to this, Vp of liquid solvent decreases while Vp of solid solvent does not. That is, equilibrium is disturbed. To restore equilibrium, Vp of solid solvent has to be decreased, which is possible only by decreasing the temperature, that is, Vp is depressed. Vp is depressed. Now we'll take up the graph as we did in case of elevation and boiling point. You please keep on drawing the graph. At the same time, keep on trying to understand how I'm explaining the graph. Write one sentence. After that, we come to the graph. Graphically, variation of Vp, variation of vapor pressure with temperature and concentration and its effect on freezing point is given below. You'll be able to read it here. Again, vapor pressure versus temperature. As I said, you have to understand, although explanation never asked in the exam, but try to understand this. Let us say at this temperature, we have a pure liquid solvent, and its vapor pressure is this much. It means represented by this point. We decrease the temperature, vapor pressure will decrease. But it is found that at a particular temperature, there is sudden fall in vapor pressure. Why it is so? I'll tell you. First of all, label. This is freezing point of solvent. This temperature at which there is sudden fall in vapor pressure, this is freezing point of solvent. This part of the graph is solvent in the liquid state. This is for solvent in the solid state. Now comes the question, why is there a sudden fall in vapor pressure at freezing point? It's very simple. See, at freezing point, this substance, this solid will solvent will change from liquid to the solid state. In the solid state, forces of attraction between particles are strong. And due to sudden increase in attractive forces between particles, vapor pressure will suddenly decrease, right? Now, back to the same temperature, we add some non-volatile solute, vapor pressure will decrease. Now, this is the vapor pressure of solution. Solute has been added. We decrease temperature, vapor pressure will decrease, and the graph will be parallel to the graph for solvent. This will decrease, and it will meet the graph at this point. This is graph for solution number 1. This is freezing point of solution 1. This difference, this is delta TF. Delta TF means depression in freezing point. Delta TF of solution 1. Right? This is delta TF. Now, to solution number 1, if I add some more solute, that is, I make the solution more concentrated, vapor pressure will further decrease. Now, in this case, when I decrease temperature, you can see this solution will boil, will freeze at a still lower temperature. So this is solution number 2. This is freezing point of solution 2, and this gap, this much, this is delta TF of solution 2. It means more the concentration of solution, higher is the value of depression in freezing point. And this is the reason mathematical expression will be exactly the same as for elevation in boiling point. Right? Right on. It is clear from the graph. It is clear from the graph that the value of delta TF, and concentration of solution are directly proportional to each other. And mathematically, delta TF proportional to molality, or delta TF is equal to constant. Earlier the constant was Kb, now the constant is Kf, is equal to delta TF is equal to Kf into, will expand molality W by MB into 1000 divided by WA. Third colligative property, first equation, to labeling equation 3a. Wait a minute. Yes. Now this constant, this is called molar freezing point depression constant. Two more terms which you need not write: molar freezing point depression constant, or freezing point depression constant, or depression constant. But one more special term you must write, also called CRYO scopic, cryoscopic constant. cryoscopic constant. Again, the definition on the basis of this equation, similar definition as we did earlier. That Kf is defined as the depression in freezing point of solvent in the solution whose molality is 1. Whose molality is 1. Its units are, I think earlier in elevation and boiling point, I probably made a mistake. I wrote the units for this. I think so. Right? But those units were for KB. Please make the correction. So units for KF are again the same. Units of KF, K by M, Kelvin per molal or Kelvin kg per mole. Now coming to the dependence of KF, again similar as in case of KB. Next paragraph. Value of KF depends on the nature of solvent as given below. Nature of solvent as given below. KF is equal to mR TF square divided by delta H fusion multiplied by 1000. I think in the numerator, you could understand everything. M is same as earlier. R is gas constant. Earlier it was TB. Now this is TF. It means what is this? This is freezing point of solvent. And this is enthalpy of fusion of solvent. And this is equation number 3b. Depression is always subtracted. It means freezing point of solution is equal to freezing point of solvent minus delta TF. Minus delta TF. We'll solve one numerical on this. Yes. Same numerical has been on WhatsApp. It has gone 2 times. Please find yourself. Okay, the numerical is calculate freezing point of an aqueous solution, 2 kilograms of which contains 50 grams of non-volatile solute, molecular weight 200. No, the other one. Calculate freezing point of an aqueous solution of glucose containing glucose and water in 1:50 molar ratio. KF is given. Please check which one did I share. No. Please ignore this one. We are not solving this one. I'll share the other one. This will be sharing. This will be solving later on. For the timing, will be solving for one solvent. Wait a minute. We'll be solving numerical number 26. 27 will be solving after this. Yes, you can see numerical number 26. Calculate freezing point of an aqueous solution of glucose containing glucose and water in 1:50 molar ratio. Kf is given. So depression will be equal to Kf into molality. Molality will be 1:50 molar ratio means 1 mole of glucose. If glucose is 1 mole, then water is 50 moles, right? 1 mole into 1000 divided by weight of solvent. Weight of solvent will be 50 moles. 50 moles of water will be 900 grams of water. So this will give the value of depression, will come out to 2.067. Freezing point of water 0. From that subtract 2.067. Answer will be minus 2.067 degrees centigrade. Again, modification if there are 2 or more solutes. Same modification. Right on. If the solution contains 2 or more non-volatile solutes, then equation 3a becomes right on, delta TF is equal to Kf into number of moles of solute 1 plus number of moles of solute 2 and so on, multiplied by 1000 divided by weight of solvent. Three C, third equation of third colligative property. I've already shared the numerical. I did that by mistake. That was numerical number 27. Check your WhatsApp message. We'll solve 27 now. I hope you are able to see in your WhatsApp message. Calculate freezing point of an aqueous solution, 2 kilograms of which contains 50 grams of NV solute A, 90 grams of B. Kf is given. Molecular weights of solutes are also given. So delta TF will be equal to Kf number of moles. One solute is 50 grams divided by molecular weight. The other solute is 90 grams divided by molecular weight into 1000 divided by weight of solvent will be 2 kilograms, that is 2000 grams, minus weight of both solutes, minus 50, minus 90. Right? When you solve, it will come out to 0.75. So freezing point of solution 0 minus 0.75. Answer is minus 0.75 degrees centigrade. We'll take up one more numerical. This is an interesting one. This is numerical number 28. Yes, 28, you can see your WhatsApp message. Yes, there's It's in the chat box also. Now, before I start solving, let us look at the statement of the numerical and let me explain you something. Numerical is 2 molar aqueous solution of glucose. 2 molar means 2 moles of glucose dissolved in 1 kilogram of water, right? Is cooled to minus 7.44 degrees centigrade. It means depression and freezing point 7.44. If there's any doubt to anyone, please ask me. Value of delta TF will be 7.44. Any doubt, anyone? Okay. Calculate mass percent of water present in the solution that will separate as ice. KF is given. Don't write anything. Look at the board. On the basis of given data, if I calculate delta TF, don't think that 7.44 is delta TF. Let us say I try to calculate delta TF on the basis of remaining data. It will be 1.86 into 2 molar. 2 molar will be 2 moles of solute into 1000 divided by 1 kilogram of solvent, right? Because this is 2 molar. But if you calculate the value, this value will not be 7.44. This, I don't know what the value will be, but it will be much lesser than 7.44. Let us say it is around 4. So freezing point of the solution on the basis of data given, 2 molar solution, freezing point should be, let us say, 4, means minus 4 degrees centigrade. Now comes the main thing. If I cool the solution below the freezing point, it means if I want to attain a depression which is higher than 4, if I want to attain a depression of 7.44, for higher depression, solution should be more concentrated than this. Solution can be made more concentrated than 2 molar either by adding some more solute or by removing some solvent. Now, when the solution is cooled to minus 7.44 degrees centigrade, numerical says a part of water separates out in the form of ice. Means amount of solvent decreases, therefore concentration of solution will increase and depression of 7.44 can be achieved. For that, what will be the amount of water, percentage of water that will separate out as ice? Now we solve the numerical. Say weight of water separated as ice is equal to X gram. 7.44. Basically, I want a depression of 7.44 is equal to 1.86 into its 2 molar solution, 2 into 1000 divided by. Now, weight of solvent will decrease. It will be 1000 minus X. If you calculate X, this will come out to 500 grams. It means out of 1 kilogram of solvent, 50% will separate out in the form of ice. So the answer is ice will be 50% of solvent taken. 50%. Now, coming to the last part of this third colligative property. Applications of depression and freezing point. Applications of depression in freezing point. Number one, to prepare antifreeze solutions. To prepare antifreeze solutions, you have to write only this much. Rest I'll explain verbally, and you will have numericals on antifreeze solutions also. See, you all know, you all own a car, your parents own a car. There is a coolant used in the radiator of the car. Radiator of rather any engine, a coolant is used. If we use, what is the purpose of coolant? Coolant, number one, will always be in the liquid state because it has to circulate through the engine. And when it circulates through the engine, it will absorb heat and keep the engine within limits. It will keep it cool. Now, if water is used as a coolant in the radiator and that vehicle, that engine is to be used at a sub-zero temperature. Let us say we want to use the car at a place where temperature, atmospheric temperature is minus 10 degrees centigrade. At this temperature, water in the radiator will freeze. In the solid form, it will not be able to circulate, move to the engine. But the purpose is to keep the engine cool means this coolant should remain in the liquid state. Now comes the rule of depression and freezing point. To this water, we add a non-volatile solute and prepare a solution. This solution will have a lower freezing point than the atmospheric temperature. So I'll add so much of solute to water that the solution obtained has a freezing point lower than the freezing point of atmosphere, so that it will remain in the liquid state and it does not freeze. So that is the meaning of antifreeze solution. Second application. Before that, let me explain. See, again, related to snowfall only. If there is heavy snowfall, you might have seen, first snow is cleared from roads by using machines. When the snow is cleared, is not 100% removed, a thin layer of snow will still remain on road. And that thin layer of snow which is left behind is very dangerous because it contains solid and the liquid forms of water, and this is the reason it becomes very, very slippery. Now, how to remove that leftover snow along with water? We sprinkle sodium chloride or we sprinkle calcium chloride. Both are non-volatile solutes. These solutes will dissolve, make in a solution whose freezing point will be lower than the freezing point of atmosphere. It means that leftover snow will melt, and after melting, road is cleared. To what temperature it can clear snow, I'll give the data also. Right, second and the last application. To clear snow on roads in cold countries, sodium chloride or calcium chloride is sprinkled. It lowers the freezing point of water below the atmospheric temperature, so that snow melts away. Sodium chloride can melt snow up to minus 21 degrees centigrade while calcium chloride can melt snow up to minus 55 degrees centigrade. That's all for today's class, children. Hopefully 2 more classes for this chapter. After that, we'll start with solutions. So these 2 classes, I think Saturday and Tuesday, we should be able to finish the chapter. Right, children, you can log out.
Thank you, sir.
Thank you, sir. Bye, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Welcome.